The year is 312 BCE. Rome is no longer just a city. It is an idea beginning to take shape across the Italian peninsula, an ambition carved in stone and written in blood. But empires are not built on ambition alone. They are built on water. In the scorching summer heat, a Roman senator named Appius Claudius Caecus stands at the edge of a parched field outside the city walls, his eyes scanning the distant hills. The Tiber River runs through Rome, yes, but it is polluted, unreliable, and controlled by those who live along its banks. What Rome needs is something unprecedented, something that has never been attempted at this scale in the Western world. Rome needs water from the sky. This is not a story about pipes and channels, though those will come. This is a story about vision, the audacity to look at a mountain spring 12 miles away, and imagine its water flowing through the heart of the city that would one day rule the known world. This is the story of how Roman engineers didn't just move water. They conquered distance, elevation, and gravity itself, creating a network so sophisticated that 19 centuries later, we still struggle to fully comprehend their genius. Let us go back further, before Appius, before the aqueducts, to understand what they were solving. Early Rome was a collection of hills and valleys, a strategic position, but a difficult one for sustaining life. The 7 hills meant that while the city was defensible, water distribution was a nightmare. Rainwater collection worked when the gods were generous. Wells reached into the earth, but they ran dry in summer or became brackish and poisonous. The Tiber, that muddy serpent winding through the valley, was useful for trade, but dangerous to drink from. Diseases swept through neighborhoods. Children died of fevers no healer could cure. The elderly weakened and fell. For a city to grow, for an empire to expand, it needed water. Not just any water. Clean water. Abundant water. Reliable water that came not from the whims of weather or the charity of river gods, but from the will of human engineering. The Greeks had already experimented with bringing water over distances, using underground tunnels and inverted siphons. But the Greeks were working with different geography, different ambitions. Rome needed something grander, more permanent, more remote. They needed to make water travel not just through the earth, but over it, suspended in the air itself, defying the natural order. Appius Claudius Caecus was not an engineer by training. He was a politician, a censor, a man of power navigating the treacherous waters of Roman politics during the Republic's expansion. But he understood something fundamental. Infrastructure is power. Control water, and you control the city. Control the city, and you control the world. In 312 BCE, he authorized the construction of Rome's first aqueduct, the Aqua Appia. It would run primarily underground, a 16-kilometer channel starting from springs near the Via Praestina, sloping gradually, almost imperceptibly, downward toward Rome. The engineering challenge was staggering. The water needed to flow by gravity alone, which meant the gradient had to be precise, steep enough to keep water moving, gentle enough to prevent erosion and maintain speed control. Picture the engineers of that time, men whose names history has mostly forgotten, standing in those hills with their Groma surveying tools, cross-shaped device with hanging plumb lines, measuring angles, calculating slopes, arguing over centimeters. That would determine success or failure. They didn't have computers, didn't have laser levels, didn't have the mathematical formulas we take for granted. They had observation, experience, trial, and an almost religious devotion to measurement. They would drive stakes into the ground at regular intervals, stretch cords between them, and use water-filled channels to establish perfect horizontal lines from which they could calculate the necessary drop. For every 1,000 feet of channel, the water needed to fall between 1 and 3 feet. Any more, and the water would rush too fast, eroding the channel and arriving turbulent and dirty. Any less, and it would stagnate, become sluggish, fail to reach the city during times of low flow. The Aqua Appia was mostly underground, which meant tunneling through rock, through clay, through the bones of the Italian earth. Workers descended into these tunnels with oil lamps, their world reduced to a circle of flickering light and the sound of picks against stone. They worked in shifts, sometimes for years, creating a channel just wide enough for a man to crouch inside for maintenance, because they knew, even then, that this structure would need to last not just years, but centuries. The channel itself was lined with a revolutionary material, hydraulic cement. The Romans had discovered that mixing volcanic ash from Pozzuoli with lime created a concrete that would set even underwater, that would resist erosion, that would harden over time rather than crumbling. This was not just construction material. This was alchemy, turning earth and fire into stone, harder than stone itself. But the genius of Roman aqueducts was not just in their construction. It was in their conception, the understanding of water as a living thing that needed to be guided, not forced. Every aqueduct began with careful selection of the water source. Engineers would spend months, sometimes years, analyzing springs. They would taste the water, observe its clarity, note its temperature across seasons, measure its flow during drought and deluge. The best springs were cool year-round, clear as glass, emerging from limestone aquifers that had filtered the water through miles of porous rock. Once a source was selected, the surveying began. Teams would work backwards from Rome, establishing the elevation at the city end, then working toward the source, constantly measuring, constantly calculating. The Roman surveying tool, the chorobates, was a 20-foot-long wooden beam with water channels on top. By keeping the water level in these channels even, they could establish a true horizontal line from which all other measurements descended. The mathematics involved was profound for its time. The Romans used a fractional system where the gradient was expressed in terms of drops per length. A typical aqueduct might drop 1 unit for every 200 units of length, a gradient so gentle that to the human eye, it appeared nearly flat. Yet over miles, this added up to hundreds of feet of elevation change, enough to bring water from distant mountains into the heart of the city. But the channel was only the beginning. Along the route, every few miles, settling tanks were built, large basins where the water could slow down and sediment could fall to the bottom. These weren't just practical. They were brilliant. By removing sediment continuously along the route, the aqueduct would last longer, need less cleaning, deliver clearer water. The Romans understood that prevention was cheaper than cure, that building quality into the system saved labor later. The Aqua Appia proved the concept, but it was underground, invisible, easily overlooked. The true monuments to Roman engineering genius would come later, when aqueducts needed to cross valleys, when channels needed to bridge rivers, and gorges, when the water needed to travel not through the earth, but high above it. Enter the arcade, the series of arches that we now immediately associate with Roman aqueducts. The first time a Roman engineer proposed building a water channel on top of a line of stone arches stretching across a valley, it must have seemed insane. Stone doesn't bend. Stone stacked too high crumbles under its own weight. How do you create a structure tall enough to maintain the gradient, strong enough to support tons of flowing water, stable enough to last through earthquakes and storms and the centuries themselves? The answer was the arch. The arch is one of humanity's most elegant inventions, a way to distribute weight outward and downward rather than crushing what lies beneath. The Romans didn't invent it. The Etruscans and others used arches before them, but the Romans perfected it, understood its mathematics, and deployed it on a scale never before imagined. A Roman arch is a semicircle of carefully cut stones called voussoirs, each one tapered so that it's wider at the top than the bottom. They're laid in sequence around wooden scaffolding called centering. The final stone, the keystone, is dropped into place at the top center, and suddenly the arch becomes a single structural unit, each stone locked in place by the pressure of its neighbors. Remove the centering, and the arch stands on its own, stronger than any single stone, capable of spanning vast distances. But one arch isn't enough to cross a valley, so they built them in series, tier upon tier. The Pont du Gard in southern Gaul, built around 50 CE, stands nearly 50 meters high, with 3 tiers of arches stacked on top of each other. The bottom tier has 6 massive arches, each one nearly 20 meters wide. The middle tier has 11 smaller arches, and the top, where the water channel runs, has 35 delicate arches, each one perfectly aligned with those below. Standing beneath the Pont du Gard is like standing beneath proof that humans can achieve anything. The structure carries no mortar. The stones are cut so precisely that they hold themselves in place through friction and gravity alone. Each block weighs up to 6 tons. The precision required to shape them, to place them, to create a structure that has stood for 2,000 years through floods, earthquakes, and wars is staggering. The water channel on top of the Pont du Gard is barely a meter wide, lined with waterproof cement, covered with stone slabs to prevent evaporation and contamination. It drops a mere 2.5 centimeters every 100 meters, so subtle that you'd never notice it walking alongside, yet precisely enough to keep 50,000 cubic meters of water flowing toward Nimes every single day. By the time of the Roman Empire's height in the 2nd century CE, 11 major aqueducts fed Rome. Together, they brought more than 1 million cubic meters of water into the city daily, more water per capita than many modern cities receive today. But where did all this water go? Understanding the distribution system reveals another layer of Roman genius. The aqueducts terminated at Castella Acqui, distribution tanks positioned at high points around the city. These were not simple reservoirs. They were control centers, engineered structures with multiple outlets at different heights, each controlled by bronze valves. The water was divided by priority. The bottom outlets fed the public fountains that provided free water to every neighborhood because Rome understood that a population with clean water was a healthy, stable population. Middle outlets fed the public baths, those great social centers where Romans of all classes came to bathe, gossip, do business, and simply be Romang. The top outlets fed private homes, but only for those wealthy enough to pay for the privilege and powerful enough to receive permission from the water board. This wasn't just engineering, it was social engineering. The system automatically prioritized public needs. During droughts, when water levels dropped, private homes lost their supply first. Then the baths would reduce their flow, but the public fountains would continue flowing, ensuring that no Romang, no matter how poor, would go thirsty. The public fountains themselves were works of art, bronze spouts shaped like lions or dolphins or gods, constantly flowing into basins where people came with jugs and buckets. There were more than 1,000 of these fountains throughout Rome, positioned so that no resident was ever more than a few minutes' walk from clean water. The baths were even more impressive. The baths of Caracalla could accommodate 1,600 bathers at once. They had cold pools, warm pools, and hot pools heated by a hypocaust system raised floors beneath which hot air from furnaces circulated. They had fountains, waterfalls, and even swimming pools. All of this required constant water flow, which required precise pressure management, which required those distant aqueducts to maintain their gentle, perfect gradient over miles of terrain. Roman engineers didn't have calculus. They didn't have fluid dynamics equations, but they understood water with an intimacy born of observation and necessity. They knew that water in a channel flows fastest in the center and slowest near the walls and bottom due to friction. They knew that curves needed to be gentle because sharp turns created turbulence that slowed flow and eroded channels. They knew that the cross-sectional shape mattered. A semicircular or arched channel moved water more efficiently than a rectangular one. Most impressively, they understood the relationship between cross-sectional area, gradient, and flow rate. A channel twice as wide didn't carry twice as much water. It carried more than twice because the additional width created less proportional friction. They used this knowledge to design channels that could be partially closed during low-demand seasons while maintaining adequate flow. The Roman engineer. Vitruvius wrote about these principles in his work, De Architectura, around 15 BCE. He described how to survey routes, how to calculate gradients, how to build settling tanks and distribution systems. But more than that, he described the mindset required: patience, precision, and respect for water's nature. Another engineer, Frontinus, appointed water commissioner of Rome in 97 CE, conducted a comprehensive audit of Rome's water system. His report, De Aqueductu, gives us astonishing details. He documented each aqueduct's length, capacity, and condition. He uncovered massive fraud, illegal taps, bribed officials, citizens stealing water meant for public use. He calculated that Rome was losing more water to theft and leakage than it was delivering, and he set about fixing both the infrastructure and the corruption. Frontinus wrote with pride about his work, but also with reverence for the engineers who came before him. He understood he was not building for his generation alone, but for centuries to come. Compare such numerous and indispensable structures carrying so much water with the idol pyramids, or the useless but famous works of the Greeks, he wrote, and there is no boasting in his tone, only the quiet confidence of a man stating an obvious truth. But even the greatest infrastructure fights a constant battle against time, nature, and entropy. The most insidious enemy of an aqueduct was something almost invisible: calcium carbonate deposits, what we call limescale. Water flowing from limestone springs carried dissolved calcium. As it flowed through the channel, especially where it slowed or warmed, some of this calcium would precipitate out and stick to the channel walls. Over decades, these deposits grew, slowly constricting the channel like plaque in an artery. The Romans fought back with maintenance crews that would enter the channels during seasonal shutdowns and chip away the deposits. Some aqueduct channels show deposits half a meter thick in places decades of buildup before cleaning. In some sections, the buildup was so severe that maintenance crews actually carved new channels through the deposit rather than removing it all. Then there was structural damage. Earthquakes could crack channels, shifting foundations by just centimeters, but disrupting the critical gradient. Tree roots could penetrate underground sections. Frost could split stones in winter. Each issue required constant vigilance, constant repair. The Aqua Claudia, started by Emperor Caligula and completed by Claudius in 52 CE, faced particular challenges. It was the longest aqueduct serving Rome, drawing water from springs nearly 70 kilometers away. Portions ran on arches more than 20 meters high. The engineering was magnificent, but the maintenance was endless. Within decades of completion, major repairs were needed. Emperors would boast of restoration work, adding their names to inscriptions, but these weren't vanity projects, they were necessities. For centuries, the aqueducts were maintained. Through political upheavals, through civil wars, through the transformation from republic to empire, the water kept flowing. The aqueducts were one of the constants that made Rome Rome, that enabled a city of 1 million people to exist in an era when most cities counted their populations in the thousands. But nothing lasts forever. As the Western Roman Empire weakened in the 4th and 5th centuries CE, as invasions increased and civic resources dwindled, maintenance declined. When the Goths besieged Rome in 537 CE, they did something brilliant and terrible. They cut the aqueducts. They knew they couldn't easily breach the massive walls, but they could deny the city water. The Byzantine general Belisarius managed to restore some water flow, but the damage was lasting. Without proper maintenance, without the organized teams of engineers and workers, the aqueducts began to fail. Channels clogged, arches crumbled. The precise gradients that took years to survey were lost to earthquakes and settling foundations. By the medieval period, Rome's population had collapsed to fewer than 30,000 people, huddling among the ruins of what had been the world's greatest city. The massive bath complexes stood empty. 1,000 public fountains ran dry. People drew water from wells and the Tiber again, just as their ancestors had done 1,000 years before the first aqueduct. The aqueducts themselves became ruins, romantic and mysterious. The great arcades stretching across the countryside were quarried for building stone. Some sections were converted into housing. Local legends grew giants must have built these, or ancient magicians. The engineering knowledge behind them seemed impossible to medieval minds. But they didn't disappear entirely. The channels remained, following their ancient paths. The springs they had tapped continued to flow, and in some sections, portions of the aqueducts were restored and continued to supply water, though never at the scale or sophistication of the Roman era. Have you ever wondered how ancient Rome, a city of over 1 million people, managed to stay so clean and vibrant? The secret wasn't just good governance or military might. It was flowing water, and lots of it. Today, we're diving deep into the incredible story of Roman aqueducts, the engineering marvels that were the lifeblood of an empire. Let's start our journey not in ancient times, but much later, during the Renaissance. Imagine walking through Rome in the 15th century. The magnificent ruins of the ancient city are all around you, half buried and overgrown. Artists and architects like Leonardo da Vinci and Michelangelo were rediscovering the genius of classical art and architecture. But it wasn't just the Colosseum or the Pantheon that captured their imagination. They were equally fascinated by the crumbling arches of the ancient aqueducts snaking across the countryside. These Renaissance thinkers saw them as more than just picturesque ruins. They were a puzzle, a testament to a lost golden age of engineering. They sketched them, studied their construction, and tried to understand how they worked. This wasn't just academic curiosity. Rome was growing again, and it desperately needed a reliable water supply. The medieval system of wells and river water was just not cutting it. This brings us to a pivotal moment in the late 16th century. Thanks to a man named Pope Sixtus V, he was a visionary, determined to restore Rome to its former glory. And he knew that to do that, he needed water. So he embarked on an ambitious project to build the first new aqueduct in Rome in over 1,000 years, the Aqua Felice. He didn't start from scratch, though. His engineers cleverly repurposed parts of the ancient Aqua Marcia and Aqua Claudia, incorporating their sturdy foundations and arches into the new structure. It was a symbolic act, connecting the new papal Rome directly to the legacy of the ancient emperors. The Aqua Felice was a triumph, bringing fresh water gushing back into the city's fountains, revitalizing entire neighborhoods. This project kicked off a new era of aqueduct building and restoration that would continue for centuries. The Renaissance sparked the interest, but it was in the 19th and 20th centuries that our understanding of these structures truly deepened. This was the age of modern archaeology. Scholars and engineers began systematic studies, not just admiring the aqueducts, but meticulously measuring them. People like Thomas Ashby, a British archaeologist, spent decades walking the entire length of these water channels, mapping their routes and documenting every detail. They excavated tunnels, analyzed the mortar, and deciphered inscriptions left by the original builders. What they uncovered was mind-blowing. They realized that Roman engineering wasn't based on rough estimates. It was incredibly precise. Let's take two of the most famous examples, the Aqua Claudia and the Aqua Marcia. These weren't just simple ditches. The Aqua Claudia, completed around 52 AD, stretched for nearly 70 kilometers. Most of it was underground, but its final approach to the city featured those iconic, towering arches we all recognize. The Aqua Marcia was even longer, running for over 90 kilometers. The precision came down to the gradient. The channels had to slope downwards, just enough for gravity to pull the water along, but not so steeply that the water would flow too fast and erode the channel. We're talking about a drop of just a few meters over many kilometers. To achieve this, Roman surveyors, using simple tools like a groma for right angles and a chorobates, which was essentially a long level, had to be masters of their craft. They plotted the course across hills and valleys with astonishing accuracy. One of the most brilliant aspects of their design was foresight. The Romans didn't just build for the needs of their time. They built for the future. They consistently over-engineered their aqueducts. The Aqua Claudia and Marcia, for example, could deliver a combined total of nearly 400,000 cubic meters of water per day. That's enough to fill over 150 Olympic-sized swimming pools every single day. For the population of Rome at the time, this was an extravagant amount of water. It shows a level of long-term urban planning that is just staggering. They knew the city would continue to grow, and they made sure its infrastructure could support that growth for generations to come. Now, let's get into the really clever engineering tricks. How did they get water across a deep valley? Building a bridge of arches dozens of kilometers long wasn't always practical. So they used a device called an inverted siphon. It sounds complex, but the principle is simple. They would build a header tank on one side of the valley and run sealed pipes, often made of lead, down the slope and up the other side to a receiving tank at a slightly lower elevation. The pressure from the water in the header tank would force the water up the other side. It's the same principle that makes water find its own level. Building pipes that could withstand that immense pressure was a huge challenge, and it shows their advanced understanding of hydrostatics. They even accounted for things like temperature changes. An aqueduct stretching for miles would expand in the summer heat and contract in the winter cold. If the structure was too rigid, this would cause it to crack and fail. So, Roman engineers incorporated what we would now call expansion joints. They would build sections of the channel with slight gaps, often filled with a flexible material, allowing the structure to breathe with the changing seasons. This is a concept that modern bridge and building engineers still use today, and the Romans were doing it 2,000 years ago. So, with all this water flowing into the city, what was it all for? This is where we see the profound social impact of the aqueducts. This abundance of clean, fresh water completely transformed Roman life. First, there were the famous Roman baths, the thermae. These weren't just places to get clean. They were massive public community centers. You could exercise, get a massage, read in a library, conduct business, and socialize, all while enjoying pools of varying temperatures. This level of public hygiene was unprecedented in the ancient world and was only possible because of the constant, massive supply of water from the aqueducts. Then there were the fountains. Rome was famous for its hundreds of public fountains, providing free, clean drinking water for everyone. Unlike in many other ancient cities where you had to rely on dirty wells or buy water from vendors, any Roman citizen could walk to a nearby fountain and get fresh water. Many grand, ornate fountains also served as public art, beautifying the city and demonstrating the emperor's generosity and power. The Trevi Fountain, though a later creation, stands in a spot fed by a restored ancient aqueduct, continuing this grand tradition. The water also flowed into public latrines, which, while maybe not the most glamorous topic, were a huge step forward for sanitation. Having continuously flowing water to flush away waste significantly reduced disease and improved public health. Wealthy Romans could even have water piped directly into their private homes, a luxury that was the ultimate status symbol. But the impact went beyond the city walls. The water was also used for agriculture, irrigating fields and market gardens in the suburbs of Rome, ensuring a steady supply of fresh produce for the massive population. It powered mills for grinding grain into flour, a crucial industrial application. The aqueducts didn't just make Rome a healthier and more beautiful place to live. They made it a more productive and resilient one. In the end, the story of the Roman aqueducts is a story of vision, ingenuity, and the transformative power of infrastructure. They weren't just structures of stone and mortar. They were the circulatory system of an empire, carrying the lifeblood that allowed Roman civilization to flourish. From the Renaissance popes who sought to recapture their glory to the modern archaeologists who decoded their secrets, these ancient marvels continue to inspire awe and admiration. They are a powerful reminder that sometimes the most profound innovations are the ones that bring the simplest necessities of life, like a clean drink of water, to everyone. Thanks so much for watching. If you enjoyed this journey back in time, don't forget to hit that like button and subscribe for more stories about the wonders of the ancient world. See you next time. Today, pieces of Roman aqueducts still stand throughout what was once the empire. The Pont du Gard draws tourists by the thousands, who walk across it or float beneath it in kayaks, marveling at stones that have defied gravity for 2 millennia. In Rome, sections of the Aqua Claudia and Aqua Agno Novus remain, their arches marching across the Campania like a procession of ghosts. Some are still functional. The Aqua Virgin, built by Marcus Agrippa in 19 BCE, still carries water to Rome's fountains, including the Trevi. Water that fell as rain on the hills outside, Rome that percolated through limestone aquifers that emerges at the springs. Agrippa's engineers selected flows through channels those engineers built, and emerges in the heart of the city, still clean, still cold, still performing the task it was assigned before the birth of Christ. Modern cities have learned from Rome, though we sometimes forget the lessons. We understand that infrastructure is the foundation of civilization, that water must be managed carefully, that shortcuts in construction lead to centuries of problems. The massive aqueducts feeding Los Angeles or New York or Tokyo are descendants of those Roman channels, gigantic versions of the same principle. Find water where it is abundant and bring it to where it is needed. But we've lost something too. Roman aqueducts were built to last forever, with materials that would improve with age, with maintenance plans built into the original design, with beauty considered essential rather than optional. We build for decades, they built for millennia. We hide our infrastructure underground and make it invisible. They celebrated it with monumental architecture. We treat infrastructure as expense. They treated it as investment in eternity. There is something profound about standing in the shadow of a Roman aqueduct. These structures were built by a civilization that no longer exists, using tools we would consider primitive for people who have been dust for 17 centuries. Yet the water still flows, or could flow again if the channels were cleared. The arches still stand. The gradient is still precisely calculated into the stones. The Romans who built these were not superhuman. They were people like us, with the same biology, the same intelligence, the same capacity for reason and invention. What they had was vision, the ability to imagine not just what was, but what could be. They looked at mountains and valleys and saw not obstacles, but roots. They looked at springs and saw not just water, but the future health of millions. They looked at stone and saw not just weight, but strength. And they had something else, something we desperately need to remember. They built for the future, for people they would never meet, for a world they would never see. The engineer who calculated the gradient for the Aqua Claudia in 40 CE knew he would live to see it completed. The workers who carved channel through solid rock knew their own children would barely see any benefit from their labor. But they built anyway, because they understood that civilization is not a transaction but a chain, each generation receiving from the past and giving to the future. Every time you turn on a tap and clean water flows, you are benefiting from an idea that Romans perfected 2,000 years ago, that everyone deserves clean water, that engineering can conquer geography, that infrastructure is the foundation of everything we call civilization. The aqueducts are monuments to human ambition, to the power of organized knowledge and labor, to the possibility of building things that will outlive empires. They teach us that the challenges we face bringing resources to where they're needed, planning for populations not yet born, building infrastructure that will serve not just us, but our descendants. These are not new challenges, and they are not impossible. In an age where we debate whether we can afford to maintain our infrastructure, where we cut corners on construction to save money, today while costing fortunes tomorrow, where we plan for the next quarter instead of the next century, perhaps, we need to stand beneath those ancient arches and remember what humans are capable of when they build not just for themselves, but for the ages when they understand that the greatest legacy is not monuments to power, but gifts to the future, when they realize that the water flowing through those channels is the same as the water that sustains us now, precious, essential, and worth any effort to preserve and deliver with care. If those ancient engineers could conquer mountains and valleys with nothing but genius and determination, armed only with observation and calculation, what might we accomplish with all our modern tools if only we had their vision, their patience, and their commitment to building not for today, but for forever?